everyone. This is a presentation dealing with recent projects related to CubeSat that we have carried out at the University of Naples. First of all, just to present ourselves, we are the aerospace system teams of the University of Naples. We are a relatively wide team. We carry out research activities in different fields of aerospace systems, as you can see, so UAVs, space systems in general, remote sensing. To tell you the truth, we do not have a long tradition with CubeSat programs, but we are trying to recover this gap. So formation flying of CubeSat assemblies is a project funded by the Italian Ministry of Education and Research. We coordinated the project as a University of Naples, and as you can see, this is the team of the project. You can probably recognize some other Italian universities, some SMIs, and big companies. The main goal of the project is to investigate the possibility to realize CubeSat missions by a fully modular design. Okay, for some specific applications like remote sensing, formation flying in general, and formation flying for specific activities like in-orbit servicing and active debris removal. So when we say modular in the context of this project, we mean that we would like to realize a satellite connecting all together modules, where modules may be subsystems or equipment that can be interpreted as a sort of bricks. Okay, so you can realize your satellite connecting those bricks that are of standard size, so 1U, 2Us, or N-Us, depending on the cases. Within this approach, we are not trying to optimize the satellite from the point of view of mass and volume. This is impossible with a modular approach, but we would like to speed up the process of design and realization. The idea is that depending on the mission, you would like to connect those modules with very limited or no customization. Okay. Within these activities, we realized some prototypes or breadboards for some modules. For instance, the onboard data handling modules that must be able to implement the modular logic in the same way as when you connect a USB device to a laptop. This must be the same for your satellite. When you connect a new module, it must be automatically recognized and configured. Okay. In this presentation, however, I would like to spend a few words on the antenna module, and more important, on the relative navigation module that was realized in our lab. Just to give you an idea of the type of realization, this is an example of a platform layout for a remote sensing mission. You can recognize the structure of different modules. This is a 12U CubeSat. It's not the standard form factor for a 12U CubeSat, but in that mission that was focused on remote sensing by more platforms, even if the form factor was not standard, the 4 satellites of the mission could be deployed using a standard carrier, such as the one produced by the Orbit in Italy. This is an example of the antenna module for which a prototype was realized by the partners of the project. It's a 3U module that is housing the antenna in the stowed configuration. And then once deployed, it's like an umbrella. You have an active feeder and a parabolic reflector. Using just a 3U unit, you can obtain an antenna with 1 meter diameter that can be used for X-band applications for both radars and telecommunication. The overall antenna is weighing less than 3 kilos. Okay. Then a few words more on the relative navigation module. This is intended for missions like proximity operations. The idea is that you would like to measure range and relative altitude, so to perform pose estimation of an approaching satellite. The system is designed to guarantee high accuracy when the distance is below a few tens of meters, so centimeters accuracy in the distance and fraction of degrees in relative altitude. The system is based on a laser. Laser is used as a ranging system and as an illuminator of a number of markers that are placed on the satellite you would like to approach. Okay, so it's passive, but you are assuming that the satellite is in some ways cooperative. Okay, laser is so used for ranging and for illuminating the object. So the infrared energy reflected from the object is then collected by a camera to perform pose estimation. We realized a breadboard of the unit of the laser in a 1U configuration, as you can see on the left, and on the camera within another U configuration on the right. Okay. These are some experiments that we performed in our GNC lab. You can see mounted on our optical bench a mock-up of a satellite where you can see the markers, okay, laser reflectors. Then you have the laser and you have the camera. This is an example of an experimental acquisition. You can see markers. So there is a target detector algorithm which is working on this image. Sometimes you can see some outliers, as in this case, by the way, based on the relative configuration between the markers, the outlier can be, we can say, easily removed. Okay. Based on our experimental analysis, we realized that the system can work fine. Okay. There are some experimental results here. Basically, we computed the relocation error after pose estimation by our camera, and the reprojection error is always below 1 pixel of the camera. This means that the system is in some ways working at the limit of the resolution of the camera that we are using. Okay. So this is more or less what I would like to share with you concerning FORCE project activities. I will go pretty fast. Okay. The last year, during our space system course, we organized a contest with our students. Students were organized in teams. We have more or less 100 students organized in 9 teams. Each one was asked to design a CubeSat mission with a maximum constraint on the size of the CubeSat, no more than 3U. And their work was inspired by the Fly Your Satellite ESA programs in terms of the way they needed to present their results and the report they were asked to write. So our students invented a number of missions. For instance, Sunflower, that was very interesting. It was based on the space demonstration of a 2 degrees of freedom solar array assembly that has been never used on this class of CubeSat to try to increase the power that you can generate. There are other missions, I don't know. DynamoSat was also very interesting. The idea was to try to exploit the tumbling motion of the satellite to generate additional power for your satellite. And just as another example, Efesto was also interesting. It was aimed at a demonstration of active debris removal. So the CubeSat is expected to deploy a sphere, and this sphere is then caught by a smart memory alloy net to perform this type of demonstration. A student competed into a contest, so a number of missions were selected as a winner, but most important from our perspective, they successfully passed the exam. After the exam, a group of 30 students was generated and was organized under our supervision. So they are continuing their CubeSat activities even beyond their student career. Their goal is to try to realize this 3U CubeSat mission that is called Daphne. Daphne is based on three main types of applications and goals. From one side, they would like to perform an experiment of shielding against space environment radiation. On the second, as a second application, they would like to perform an IoT experiment using LoRaWAN standard. So trying to upload commands and download telemetry from home, basically. And the last part of the mission, while the satellite is re-entering the atmosphere, so it is very low orbit, they would like to perform some type of ionospheric environment characterization. So our students are currently looking for funding to trying to complete this type of program. Okay, so that's all from my side. I didn't check time, but I assume I was pretty in time. So I hope you enjoyed my presentation, and I'm here to ask your question.